This section is IP addressing and details the role of IP in TCP/IP networks, as well as the general characteristics of IP and the use of IP addressing to support logical data forwarding between networks. The Internet Protocol, or IP, is designed to provide a means for internetwork communication that is not supported by lower layer protocols such as Ethernet. The implementation of logical IP addressing enables the Internet Protocol to be employed by other protocols for the forwarding of data in the form of packets between networks. So a strong knowledge of IP addressing must be attained for effective network design, along with a clear familiarity of the protocol behavior, to support a clear understanding of the implementation of IP as a routed protocol. So upon completion of this section, it is expected that trainees will be able to describe the fields and characteristics contained within IP, distinguish between public, private, and special IP address ranges, successfully implement VLSM addressing, and explain the function of an IP gateway. In the previous section, we introduced how the frame is capable of referencing the next set of instructions, or header, that is to be processed through the type field. Often this next header refers to IP and is defined using the 0800 hexadecimal value. So this section introduces the Internet Protocol, or IP, that represents one of a number of protocols within the TCP/IP protocol suite that are used for achieving end-to-end delivery of data over a logical path. In terms of Ethernet and the data link layer, the objective was to ensure data reached the intended destination over the physical medium, and ensure that the frame remained intact. This section looks at how the IP header is used by the Internet Protocol following the discarding of the frame header and trailer. The IP header represents the result of encapsulation by the Internet Protocol at the network layer of the OSI reference model. The main function of the Internet Protocol is to support the logical forwarding of data between networks in a process known as routing, as well as manage the size of the data blocks as they traverse different networks, which at times requires the data blocks be broken down in a process of fragmentation. The IP header takes up at least 20 bytes of the data block size and contains a number of fields, as found with the Ethernet frame, with each field playing a role in network layer operations. The version field is used to ensure the same version of the protocol is used by the sender and receiver. The header length is expected to be a multiple of 32 bits, where a bit represents a single 1 or 0 value that is used together with other bits to represent clusters of 8 bits, or a byte, or octets as it's also known, that make up the instructions in the IP header. If the bit number should deviate from a multiple of 32 bits, the header will be considered to be corrupt. If the DS field is used for more advanced operations that improve transmission quality of select data. Older material references this as the type of service, or TOS field. However, its function in the IP header has changed somewhat and is now the DS field, where DS refers to differentiated services. The IP options field will commonly be used to carry additional information and support functions associated with other processes and applications. The size of the IP header will grow as more IP option parameters are added. The header checksum field performs a role of maintaining the integrity of the IP packet header, in pretty much the same way as the FCS field did for the Ethernet frame. For other fields, we shall detail their operation as we move through this section, starting with an understanding of the IP address that is carried within the source and destination IP address fields. The IP address is a 32-bit value that is broken into 4 octets, with each octet representing a value between 0 and 255. It is common for the IP address to be written in a dotted decimal format as we show here. However, to truly understand the behavior and function of the IP address as part of the IP protocol, it is necessary to represent the IP address in a binary format. We give an example here of a common IP address and the binary equivalent that represents the 32 bits. At a base level, IP addresses are broken down into 2 parts. The first part defines the network of the IP address, while the second part defines a specific host or interface on that network. Hosts on a network are able to uniquely represent themselves through IP addresses and can identify as to which network a host belongs. This generally means that hosts do not necessarily need to be part of the same physical segment as found with Ethernet MAC addresses, and so IP addresses are commonly referred to as logical addresses, while MAC addresses are known as physical addresses. This behavior is well demonstrated in technologies such as VLAN and proxy ARP. Well, the example here shows a host address for which a host, in this case 1, is part of network 192.168.1. Generally, all host addresses within a network are assignable, with the exception of two addresses. In binary, these are recognized in the host part of the IP address as having a binary equivalent of all zeros or all ones. In the case of the all zero host field in binary, this value is used to represent the network to which all other host addresses belong. Each network range must also support broadcasts, and does so through setting all host bits to a value of 1 in binary. As such, the upper and lowermost values in IP network address ranges are reserved, so that hosts are not assigned such addresses. So with the introduction of IP addresses, we start to see various numbering systems being used in both addressing and header fields. It is important that these numbering systems be understood, particularly in the case of binary, so that design and implementation of effective IP addressing schemes for networks can be performed. We should all be familiar with decimal, which is considered a base 10 numbering system supporting a range of values from 0 through to 9. In comparison, we can understand binary to be a base 2 numbering system, since there are only two values that can be used, either 0 or 1. Hexadecimal, on the other hand, is considered a base 16 numbering system, with values ranging from 0 to F, where A to F represent values equivalent to 10 through to 15. So we have seen hexadecimal used for MAC addresses and in the type field of frame headers, and continues to be used for other protocol headers and fields and address values. While a single binary bit value is only capable of supporting two states of either 0 or 1, a combination of two bits is capable of supporting four states of 00, 01, 10, and 11. As more bits are used in combination, the number of possible states increases twofold. It is therefore possible to represent this using the formula of 2 to the power of x, where x represents the number of bits, to determine the total number of possible states, which for a single byte or octet represents 2 to the power of 8, or 256 possible states. In IP networks, these 256 states must represent values from 0 through to 255. This is achieved by assigning a power to each bit in order to represent its value. So we show in this example 8 bits and the corresponding powers, starting from 2 to the power 0 for the rightmost bit, through to 2 to the power 7 for the leftmost bit, along with the equivalent binary value that is expressed as a decimal number, which we can see shown below. We should understand that where all binary values in an octet are set to 0, the equivalent decimal value is also 0, and where all 8 bits are set to a value of 1, the equivalent decimal value is 255. The table gives a reference between binary number patterns and the equivalent decimal and hexadecimal values. This table also helps to clearly represent the relationship between all 1 values in binary and the string of FF values seen used to represent broadcasts in Ethernet frames. So we can go ahead and apply this binary numbering system to an IP address that is represented in a dotted decimal format. In this example, the first 3 octets represent the network, while the 4th octet defines the individual hosts. For all hosts that are considered part of the same network, the binary values in the octets representing the network will be the same, while the host value will generally vary to uniquely identify each host or interface. We can use the first octet as an example of how the decimal value is determined. In this octet, only the first 2 bits are set to a value of 1. From the previous reference table, we can understand these bits to represent 2 to the power 7 and 2 to the power 6, or 128 and 64 respectively. If these numbers are added together, we get a final decimal value of 192. The same principle can be applied to the next octet, which in this case, and starting from the left, the first, third, and 5th bits have been set to 1, that represent values of 2 to the power 7, 2 to the power 5, and 2 to the power 3, or 128, 32, and 8. When added together, we get a decimal value of 168. For the final 2 octets, only the 8th bit is set. So this simply provides us with a value of 2 to the power 0, or 1. The IPv4 address range is comprised of nearly 4.3 billion addresses, which early on in the specification of IP standards was structured into classes in order to provide flexibility of host allocation, as well as define a small number of networks containing a vast number of hosts, a larger number of networks containing a considerable number of hosts, and a vast number of networks containing a smaller number of hosts. These classes are generally known as class A, B, and C. We can easily distinguish each class in binary based on the high order or leftmost bits. For class A, the high order bit is fixed as 0. For class B, the 2 high order bits are fixed as 1 and 0, while for class C, the 3 high order bits are always set as 1, 1, and 0 in that order. The number of addresses supported in each network of each class can also be determined based on the number of bits for the host portion of each class. So for example, class A allocates 24 bits for hosts per network, which equates to 2 to the power of 24, or over 16.7 million addresses. For class B, 16 bits are allocated, which provides 65,536 addresses. And finally, the class C range contains 8 bits per network, or 256 addresses. Networks have a defined range, each of which has been referenced in this example. We should notice, for example, that networks 0.0.0.0 and 127.0.0.0 are not present, since these networks represent examples of certain reserved ranges. In the case of class C, we can understand the network to range from 192.0.1.0 through to 223.255.254.255, which represents the last address in the 192.255.254.0 network. From 224.0.0.0 through to 239.255.255.255, addresses are reserved for multicast groups and are understood to be part of the class D address range, beginning in binary with a fixed high-order bit range of 1110. The range 240.0.0.0 onwards is reserved for experimental testing of protocols and will not be found in the public network domain. In the case of class C, we can understand the network to range from 192.0.1.0 through to 223.255.254.255, which represents the last address in the 223.255.254.0 network. From 224.0.0.0 through to 239.255.255.255, these addresses are reserved for multicast groups and are understood to be part of a class D address range, beginning in binary with a fixed high-order bit range of 1110. The range 240.0.0.0 onwards is reserved for future use, and until now has not been officially designated any role, and as such will not feature in any networks we may come across. Certain addresses and address ranges have been allocated to support various operations, and we highlight some of those here. The first of these is a set of private addresses found within the class A, B, and C address ranges. Since the IP address range is finite, the allocation of all IP addresses would have already occurred. The private address range, however, allows addresses in networks that are considered private, such as those found in homes and offices and restricted to a number of private users, to allocate addresses from these private address ranges. These networks can be reused across many private networks, and by doing so, has allowed the lifetime of the IPv4 address range to be prolonged. The Class A address range hosts a single private network, while Class B contains 16 private networks, and Class C hosts 256 individual private networks. Special addresses and ranges exist in support of special functions, such as in the case of the 127.0.0.0 address range that is generally reserved for diagnostics, that causes any packet sent to a destination in this range to be looped back, for which the address 127.0.0.1 is most commonly recognized and is used to resolve the local host. The reserved 0.0.0.0 address is used to represent any network within the IP address range. Its function will be made more apparent when routing processes are introduced. Finally, we highlight the network broadcast, which can be understood to be the IP broadcast address for all networks. However, such a broadcast will cause major network congestion, and so default network behavior tends to restrict broadcast to the immediate network on which a device is located. In order for communication over IP to be successful, end stations must be aware of the network to which they are addressing before forwarding is possible. We give an example here of a single collision domain on which we find hosts that are considered members of one of two different IP networks. Hosts that are part of a given network are naturally familiar with the network to which the host belongs. However, hosts are not generally aware of other hosts that belong to different networks. This means that even though hosts are part of the same physical network, they may still be logically isolated from one another. A broadcast that is sent to the destination of 192.168.1.255 will be encapsulated and broadcasted at the data link layer using the FF hexadecimal string to define that this is a broadcast frame, which at the data link layer will be received by all hosts. However, upon accessing the IP header following the discarding of the frame header and trailer, hosts in the 192.168.2.0 network will discover the destination of 192.168.1.255 intends for this packet to be received by hosts in the 192.168.1.0 network, and so will be subsequently discarded. In order to truly understand whether a packet is capable of reaching a given destination, it is necessary that the network address of the intended destination and the network address of the receiver be displayed in binary, for in which case the two addresses should be identical. In the example given, it is clear in decimal format that the addresses of the two networks are different. However, when subnets are manipulated, this may be harder to determine. The subnet mask is a 32-bit binary value that is composed of a contiguous string of bits set with a value of 1, followed by a contiguous string of bits set with a value of 0. Where the bits are set to 1 in the subnet mask, the equivalent bits in the IP address are considered to represent the network to which the address belongs, while the 0 string of bits defines the host range within the IP address. In this example, we show the association between the subnet mask and the IP address. A conversion has been performed in both instances, for which we find that the first 24 bits of the subnet mask are represented as 1 values, and denotes the bits used to represent the network, which in this case is 192.168.1. This can be represented using the format of /24, which is often referred to as the address prefix. The remaining 8 bits, which in the subnet represent a string of zeros, shows the range used for defining the host. Since currently in the IP address the host section is also listed as a string of zeros, it can be assumed that 192.168.1.0 represents a network address. A default subnet mask is what is used to define the network range for each of the 3 main IP address classes. For class A, the default subnet mask denotes that only the first 8 bits should be used to define the associated networks. For class B, the default subnet mask contains 16 bits for each network in this range, and finally 24 bits are used to represent the default subnet mask of networks found in the class C network range. As the number of bits used by the subnet mask increases, so does the number of possible networks. However, the number of possible hosts per network will be dramatically reduced. IP addressing that adheres to the principles of classes and the default subnet masks that define the structure of these classes is known as classful addressing. The establishment or maintenance of any enterprise network requires a strong understanding of addressing and subnets in order to achieve the effective design of networks through address planning and the implementation of networks based on such address plans. The subnet mask plays a major role in addressing, and we shall demonstrate in this example the extent to which the subnet mask influences addressing. We show in this example a host address of 192.168.1.7 that is part of the class C range of networks and uses the default subnet mask of 255.255.255.0. From this we can understand that the first 24 bits represent the network, with the 8 remaining bits representing the host addresses for the network. It is generally necessary when designing networks to determine the number of supported hosts for each network, to ensure that a network is capable of hosting all potential users, such as in the case of a single department of a company. The addresses that can be assigned to hosts must also be determined. Understanding this clearly requires that both the host address and subnet mask be represented in their binary form. We are able to then determine the network to which the host belongs. This is achieved by comparing each bit in the address to the corresponding bit of the subnet mask. Where both bits are set to 1, a result of 1 is attained. In all other scenarios, such as where 1 or both bits are 0, the result is also 0. The resulting 32-bit value, when converted to decimal, provides us with the network address of the host. The number of addresses supported by this can be identified using the formula 2 to the power of n, where n refers to the number of host bits, which in this case is 8. This gives us a resulting value of 256. The actual number of supported hosts, however, requires that the first and last addresses, which represent the network and broadcast addresses for the network, be excluded. In binary, these are represented as a string of zeros and as a string of 1 values in the host portion of the address. The formula 2 to the power of n minus 2 gives us the true number of supported hosts, which in this case is 254. We provide a case scenario that is based on the same principles as demonstrated in the previous example. It is expected that any individual that must work with IP networks be extremely familiar with the process of determining a network's range and the number of hosts that a given network can support. It is recommended that the recording be paused while the answers are determined. However, this should take no longer than 5 minutes for those who are new to IP addressing. The first thing we should determine is that this address is a Class B address due to the address lying in the 172 range, which if converted to binary will be found to start with high order bits of 1 and 0. In addition, the subnet mask defines 16 bits for the host, again determined by converting the mask into binary, for which the resulting string of 1 values determines the network portion of the address. To determine the network address for this host, the IP address and subnet mask should be translated into binary and compared. Where the bit value in the IP address and the corresponding bit in the subnet mask is 1, the resulting value is 1. In all other variables, the result is 0. This, when calculated and represented in decimal, should give a result of 172.16.0.0, since the last 16 bits of the subnet mask represent a string of zeros. From the subnet mask, the number of host addresses can be determined, which in this case represents a formula of 2 to the power of 16, as a result of the 16 host bits in the mask. This defines 65,536 addresses. For the number of valid host addresses, the first and last address must be deducted from this result, giving a total of 65,534 potential hosts. In truth, however, this number of hosts could never be assigned to hosts in its entirety in this current form. A single network containing a large number of hosts will be subjected to extreme congestion as hosts fight for a window of time in which to transmit data, in a process known as contention. Classful addressing also introduces other issues, which shall be introduced in the following slide. When classful addressing is used to define networks, issues of address wastage become a major concern, since address classes are somewhat fixed. Class C is fixed at 254 valid host addresses, Class B at 65,534 valid addresses, and Class A at 16,777,214 valid host addresses. When we begin to assign network ranges as part of an overall network design within an enterprise, we begin to also find that different networks have varied requirements on the number of host addresses needed. Some large departments may require many host addresses, while small departments may have a much smaller requirement. We demonstrate this case here, in which a design requires 3 networks that are capable of supporting a varied number of hosts. Where classful addressing is used, a best fit is determined, and since the host required to be supported for all networks is less than 254, Class C represents the best choice. 3 separate networks in the form of 192.168.1.0, 192.168.2.0, and 192.168.3.0 have all been allocated. However, in all cases, the fixed default mask means that 254 valid host addresses will be allocated in all instances. For the 192.168.1.0 network, only 30 host addresses are required, therefore resulting in address wastage of 224 addresses. In the case of the remaining 2 networks, the same problem is faced. In order to alleviate the problem of address wastage, more flexibility needs to be provided by the subnet mask. The default network size of a Class C network provides 256 host addresses, 254 of which are assignable, and by breaking this default network into smaller subnetworks, networks containing a more feasible number of hosts can be utilized. This is achieved by manipulating the subnet mask to break down the Class A, B, or C networks at the major network boundary and create multiple subnetworks in a similar fashion to how an orange can be broken into smaller segments. The size and number of these subnetworks depends totally on the subnet mask. It achieves this by utilizing host bits and represents these bits as a value of 1, or as part of the network, and no longer as a host bit. So as an example of this, we show here a host address of 192.168.1.7, which we used in our initial example. In that example, the class C mask of 255.255.255.0 was used, since it represents the default class C subnet mask. In this example, however, we see that the subnet mask has changed to 255.255.255.128. The first question we may ask is, where did this 128 value come from? In order to understand that, we need to go back to binary. In this example, the binary translation for address and subnet mask has been provided. When we look at the subnet mask in binary, we notice one additional bit has been assigned with a value of 1. The bit that has been assigned represents a value of 2 to the power of 7, or 128. The difference between the major network boundary and the current network represents the subnetwork range. In this case, the difference is 1 bit. To understand what subnetworks now exist, we take this subnetwork range and apply the same 2 to the power of n formula to get the result. In this case, the subnetwork range comprises of only a single bit, and so the formula 2 to the power of 1 gives us a value of 2. This represents two subnetworks, which we can further clarify since a single bit supports only two states of either 0 or 1. Next, we need to determine for each subnetwork exactly how many hosts can be supported. As before, we take the number of host bits and apply this number to the formula 2 to the power of n. Since in this case only 7 bits represent the host according to the subnet mask, we end up with a value of 2 to the power of 7, or 128 hosts. To identify the number of valid hosts, we again need to deduct the first and last host addresses from the range to get a result of 126 valid host addresses. Now, coming back to the host address of 192.168.1.7, we can apply the same comparison of the network address and subnet to determine the subnetwork to which this host belongs. Again, where the compared network and subnet binary values are both 1, the result is also 1. In all other cases, the result is 0. As we can see in the example, following the comparison, we get the displayed binary result, which when translated to decimal gives us the network address of 192.168.1.0. If we convert all host bits to 1, this will give us the broadcast address for this subnetwork, which when converted gives us a result of 192.168.1.127. For this subnetwork, the subnetwork bit is set to 0 and denotes that it is the first subnetwork address in this range, for which we can understand ranges from 192.168.1.0 through to 192.168.1.127. If this subnetwork bit is set to 1 and the host bits are 0, we get the network address of the second subnetwork with a network address of 192.168.1.128. Where all host bits are set to 1, we get the broadcast address of 192.168.1.255. And this demonstrates how the original Class C network has been broken down into two separate subnetworks. As more bits are allocated by the subnet mask, the number of subnetworks increases, while the number of hosts in each subnetwork will generally decrease. Where all subnetworks in a major network boundary are of the same size, the mask is known as a fixed-length subnet mask, while in the case where subnetworks in a major network boundary are of different sizes, meaning that the different subnetwork mask has been used for different subnetworks, this is referred to as a variable-length subnet mask, or VLSM, and represents the more common solution type of the two. We return to the network topology that was used to demonstrate the limitations of classful addressing and attempt to apply the rules of VLSM to the host ranges given. In this case, 3 individual Class C networks are not needed since all networks can be supported using a single Class C network address range, and this demonstrates an immediate optimization of the utilized address space. Using the Class C range of 192.168.1.0, it is recommended that, using the principles of what has been explained, 5 to 10 minutes be taken to attempt to allocate a valid VLSM range for each of the networks shown, beginning with the larger network that requires 30 hosts. From this, a valid subnetwork address and subnet mask should be defined. If completed successfully, a subnetwork and subnet mask should be determined for the remaining networks. Those wishing to attempt this may refer to the previous slide for support or pause the recording at this point. In order to allocate a subnetwork for 30 hosts from the 192.168.1.0 Class C range, We firstly need to determine how many host bits would be required. Previously, we determined that 7 host bits gave us 2 to the power of 7, or 128 hosts, but only 2 subnetworks. In this case, at least 3 subnetworks are needed, but in this instance, only 30 hosts need to be supported. 6 host bits would provide 2 to the power of 6, or 64 hosts, while 5 host bits gives us 2 to the power of 5, or 32 hosts, which after removing the first and last host bits, gives us exactly 30 valid hosts. That leaves us with 3 host bits that can represent the subnetworks. If we use the formula 2 to the power of n, where n represents the 3 remaining host bits, we get a result of 2 to the power of 3, or 8 subnetworks, each of which supports 32 hosts. We can confirm this by multiplying 32 by 8 to get the 256 bits that make up the Class C 192.168.1.0 range. Since 3 bits have now become part of the network range, this must be reflected in the subnet mask. Previously, only a single bit was assigned with a value of 2 to the power of 7, or 128, that changed the mask to 255.255.255.128. In this case, however, 3 bits have been allocated, representing values of 2 to the power of 7, 2 to the power of 6, and 2 to the power of 5, or 128, 64, and 32, which when added together gives the value of 224. This leaves us with a subnetwork of 192.168.1.0 with a mask of 255.255.255.224 that is capable of supporting 32 host addresses, 30 of which are assignable. The range is therefore from 192.168.1.0 through to 192.168.1.31. The next subnetwork will begin at 192.168.1.32, and with a mask of 255.255.255.224 would support another set of 32 host addresses. However, only 20 host addresses are needed. We could attempt to break this subnetwork down further. However, 4 host bits would provide only 16 host addresses, which is not enough, and so the same mask should be applied in this instance also. For the 20 hosts, a subnetwork address of 192.168.1.32 with a subnet mask of 255.255.255.224 should be used to allocate 32 host addresses from 192.168.1.32 through to 192.168.1.63. We find, however, that there are still 10 valid host addresses that are effectively wasted, meaning that even VLSM does not provide a perfect solution. However, the utilization of addresses is much more efficient, and good address design practice recommends that some addresses be available to accommodate for expansion where new hosts are required. The final network requires only 10 hosts be currently supported. Starting from the next subnetwork of 192.168.1.64, the current subnet mask allows 32 host bits to be supported. However, as mentioned, only 10 are currently needed. We have determined that 4 host bits will provide for 16 hosts, 14 of which are assignable. This would result in variation to the subnet mask, effectively invoking VLSM. 4 host bits would leave 4 bits to represent the subnetwork, with these 4 bits representing values of 2 to the power of 7, 2 to the power of 6, 2 to the power of 5, and 2 to the power of 4, or 128, 64, 32, and 16 respectively. When combined, this leaves a value of 240. As such, we end up with a subnetwork address of 192.168.1.64 with a mask of 255.255.255.240 that contains 16 host bits, 14 of which are assignable, with a network range from 192.168.1.64 through to 192.168.1.79. The remaining Class C address range from 192.168.1.80 through to 192.168.1.255 is left unused and provides addressing that can be allocated as part of any future network expansion. VLSM provides an effective solution to better utilization of address ranges in each class. However, it does not deal with all address utilization issues. A large number of mid-sized companies requiring a larger number of addresses would often turn to the Class B range, since Class C was often too small and Class A often too vast. The problem faced is that this address range is fairly limited, since it supported only 65,000 distinct networks, and utilization of the Class B range was becoming a growing concern. Each network must also be understood in the public network in order for data to reach its intended destination. Certain devices used in the public network to manage IP address path forwarding must list such networks in a table. However, as this table grows, more memory is utilized, and searching through the table becomes more difficult. The resulting solution involves transition from a classful addressing scheme to a classless one. Classless interdomain routing, or CIDR, involves the use of prefixes instead of classes, meaning that a Class C network is recognized as a network with a /24 prefix. The boundary between classes are removed, so it is possible to represent two /24 networks as a single network with a /23 prefix. Since such a prefix provides 9 host bits, that accommodates 2 to the power of 9 or 512 hosts, the equivalent of 2 Class C addresses. IP gateways are devices that are responsible for handling the forwarding of IP packets that are intended for destinations in networks that are different from the network on which the packet originated. The gateway is typically considered a Layer 3 device since it handles IP processes which associate with the network layer of the OSI reference model. Here we show 2 examples of gateways. The first involves the use of a router, which is connected directly to 2 different networks. Host A encapsulates data, which is carried as a frame over the physical medium, before reaching the IP gateway. We should assume that data is intended for host B, which lies in a different network. The gateway must determine, following processing of the frame header, whether the gateway is aware of the network to which the packet is to be forwarded. If the gateway is, the packet will be forwarded. If not, the packet will be dropped. In the second example, the gateway is a host device, for which we should note that host A belongs to network 192.168.1.0, whilst host B belongs to 192.168.2.0. Additionally, both host devices are connected to the same physical medium. Hosts are generally considered Layer 7 devices, or end stations. However, we show them here based on their roles as Layer 3 gateways. Host A contains a table that lists networks, and the interface via which frames should be forwarded, as is found with any Layer 3 device. The table, known as a routing table, must contain the network on which host B resides in order for packets to reach host B. Packets that reach host B may often require host B to reply. This means that host B must also operate as an IP gateway, and the table of host B must also contain a network entry for the network on which host A resides, in order for communication between the 2 hosts to be successful. Packets generated will typically have a packet size of 1500 bytes, which does not include the frame header. Gateway devices such as routers specify a value referred to as the maximum transmission unit, or MTU, which identifies the maximum supported size of a packet that this particular device is technically capable of transmitting. If the received packet size is larger than the supported transmitted packet size, the packet must be fragmented. Fragmentation refers to the breaking down of a packet into smaller packets before transmission across the remaining path to the intended destination at the network layer can be achieved. One key point to note is that once packets are fragmented, they remain fragmented until the packet fragments reach the intended IP destination, at which point reassembly of the fragments will occur. There are 3 key pieces of information that are needed in order to successfully fragment packets and ensure the delivery and reassembly of the packets has the best chance of success. It is firstly necessary to distinguish a packet from all other packets in the IP network. The identification field is used to achieve this, in which a 16-bit value is used to identify each packet. When fragmentation occurs, every packet fragment must be encapsulated within an IP header to support delivery to the intended destination. Upon arrival at the destination that has the same address as the destination IP address, the packets must be reassembled. The identification field is used to identify which fragments are associated with each packet. Prior to assembly, it is also necessary to determine whether all fragments have been received. If a fragment is missing, reassembly cannot be performed successfully and all fragments will be discarded. In order to determine when to begin reassembly, every packet contains a flags field, which includes a flag bit value known as the more bit, and this is used to determine whether more fragments for a fragmented packet exist. If a fragment of the packet is not considered as the last packet fragment, the more bit flag will be set to 1, to indicate that more fragments should be expected. For the last fragment of a packet, the more flag is set to 0. When a destination receives this fragment with the more bit set, the destination will know to start the reassembly of the packet. This does not guarantee that all fragments have been received, however, so it is still possible for reassembly to fail. The final problem relates to the reassembly process of the fragments. Since IP networks are considered to be packet switched, this means that there is no single path of transmission, and packets may traverse different paths in order to reach a given destination. This may result in packets being received in a different sequence order to the order in which they were transmitted. In the example given, only a single router is used and only a single path exists. However, enterprise networks may often involve greater complexity. We use the fragment offset field to identify the byte order of a fragment. The first fragment will usually start at byte 0, whilst the next fragment will start at a position equal to the total number of bytes of the previous fragments plus 1. So for example, a fragment with a size of 1260 bytes will begin at byte 0 through to 1259, for which the following fragment will show an offset of 1260. In this way, the fragment order can be maintained for all fragments. Reassembly relies on a timer that is initiated once the last fragment is received. If the packet cannot be reassembled within the time frame defined by the timer, all fragments will be discarded. The time to live or TTL field is another fail-safe mechanism supported in IP headers to ensure that packets that are unable to reach their intended destination do not become forever caught in transit over the IP network or stuck within loops, such as where two routers continually forward packets between one another. The effects of such behavior would quickly result in congestion within the IP network and high utilization of system resources. The TTL is defined within an IP header for every packet that is generated, and for which the value of the TTL can vary. Commonly, the TTL value begins at 255 and is decremented prior to forwarding by each layer 3 device the IP packet traverses. In the example, we can see that host A has generated a packet containing a TTL value of 255. Once this is transmitted, routers along the path to host B receive the IP packet and assign a new IP header as part of the encapsulation process, during which time the TTL value is decremented by 1. This process continues across the entire path to the destination. If the TTL happens to reach 0 before the intended destination is reached, however, the packet will be discarded, and notification of this packet loss will be supported by another protocol called ICMP, which is introduced in the next section. Finally, we highlight the protocol field, which operates in a manner very similar to that of the type field found within the frame header. Once processing at the IP layer has been completed, it is necessary to determine the next protocol to which the data should be forwarded. The protocol need not necessarily be at the upper layer. We see in this example some common protocols that are referenced within the protocol field of the IP header, such as TCP and UDP, which are found as part of the transport layer, or ICMP, which is considered to operate on the same layer as IP. As with the type field, the protocol field uses hexadecimal values to identify the different protocols to which the data is to be forwarded. So in summary for this section, then, we ask 3 questions here. The first of those is, what is the IP subnet mask used for? Well, the subnet mask is a crucial part of IP addressing, and is used to define the structure of an IP address and allow the boundaries of a network to be clearly defined. As we have seen, subnet masks can be manipulated to flexibly define subnetworks in order to improve the utilization of IP addresses as part of network design. Subnet addresses are further implemented to specify address prefixes as part of the classless addressing and the aggregation of networks as part of the classless interdomain routing, or CIDR. What is the purpose of the TTL field in the IP header? Well, the TTL is primarily designed to limit the capability for IP packets that are unable to reach the intended IP destination to become infinitely caught in the IP network. The TTL is capable of assigning a lifetime to such packets so as to ensure that the IP network does not become congested with these packets. Finally, then, we ask, how are gateways used in an IP network? Well, the IP gateway can be understood as the boundary between different IP networks. And for packets to reach networks that other than their own, it is necessary that traffic firstly traverse such gateways. Gateways have the added feature of controlling the flow of IP broadcasts to ensure that packets set to be broadcast are generally restricted to the local network.